the Mitsubishi A6M Zero should have been impossible. American intelligence officers reviewing reports from China in 1940 dismissed it as propaganda. A carrier-based fighter with the range of a bomber, the agility of an acrobat, and a climb rate that defied physics. The numbers looked fabricated. The claims seemed desperate. Until December 7, 1941, when 125 Zeros descended on Pearl Harbor and proved every impossible specification to be cold, measured fact. Before we go deeper into how this decision changed the Pacific War forever, make sure to subscribe for more history that actually happened. The Imperial Japanese Navy in the mid-1930s understood that war with the United States or Britain would be decided by carrier aviation. Japan's industrial base could not match Western production. Japan's oil supplies depended on imports. Japan's strategic position required offensive operations that could destroy enemy fleets before they closed to battle range. This doctrine demanded aircraft with capabilities no existing fighter possessed. The Navy needed a weapon that could escort bombers on strikes reaching 700 nautical miles from the carrier, fight its way through enemy defenses, and return with enough fuel reserve to find the carrier in poor weather or after dark. It needed maneuverability to defeat enemy fighters in combat. It needed speed to catch enemy bombers. It needed armament to destroy both fighters and bombers. And it needed to operate from carrier decks with short takeoff runs and precise landing approaches. The existing Type 96 carrier fighter, designed by Mitsubishi and introduced in 1936, met some requirements. It was highly maneuverable and had performed well in operations over China. But its fixed landing gear created drag that limited speed to 270 miles per hour. Its range was insufficient for long-distance escort missions. Its two 7.7mm machine guns lacked stopping power against modern bombers with defensive armor. The story begins not with Pearl Harbor but with a sheet of paper dated October 5, 1937. The Imperial Japanese Navy's Bureau of Aeronautics issued document planning requirements for the prototype 12-ship carrier-based fighter, a 14-point specification that aviation engineers at both Mitsubishi and Nakajima Heavy Industries read with something between disbelief and despair. The Navy demanded a carrier fighter with a maximum speed of 500 km per hour at 4,000 meters. It needed to climb to 3,000 meters in less than 9.5 minutes. Combat radius had to support operations 1,200 kilometers from the carrier. Two 20mm cannons. Two 7.7mm machine guns. Maneuverability superior to the Type 96 carrier fighter it would replace. And all of this in an aircraft that could operate from the 180-meter flight decks of Japan's carriers with full armament and fuel. The competition between Mitsubishi and Nakajima reflected Japan's approach to military procurement. Rather than selecting a single contractor, the Navy issued requirements to multiple firms and accepted competitive designs. This created redundancy and encouraged innovation. It also divided limited engineering resources across parallel programs. Nakajima Heavy Industries, Japan's largest aircraft manufacturer, employed more than 40,000 workers across multiple facilities. The company produced engines as well as airframes and had extensive experience with radial engine installations. Nakajima's engineers reviewed the 12-ship specification and concluded that meeting the range requirement while maintaining the required speed and maneuverability exceeded the capabilities of available engine and materials technology. The calculations showed that to achieve the Navy's range targets, the aircraft would need to carry more than 500 liters of fuel internally, plus provisions for external tanks. This fuel load, combined with the required armament and structure strong enough to survive carrier operations, would push gross weight beyond 2,800 kilograms. Available engines could not push this weight to the required speed. Nakajima withdrew from the competition within weeks. Their engineers calculated the requirements and concluded they were mutually exclusive. The laws of aerodynamics and material science could not be bent far enough to accommodate what the Navy wanted. Mitsubishi's chief designer, a 34-year-old engineer named Jiro Horikoshi, thought the requirements were nearly impossible. Nearly. He assembled a team in January 1938 at Mitsubishi's Nagoya plant and began the systematic dismantling of every assumption about what a fighter aircraft had to be. Horikoshi understood that conventional approaches to fighter design could not satisfy the Navy's requirements. Every major air force in the late 1930s prioritized speed and firepower. The British Spitfire used a Rolls-Royce Merlin engine producing 1,030 horsepower to achieve speeds exceeding 360 miles per hour. The German Messerschmitt Bf 109 used a Daimler-Benz engine producing 1,100 horsepower. American fighters like the P-36 Hawk used engines approaching 1,200 horsepower. All of these aircraft accepted combat ranges under 400 miles. They sacrificed range to maximize speed and climb performance. Japan's engine industry could not match Western power outputs. The Nakajima Seiki represented the most advanced Japanese radial engine, but its two-row, 14-cylinder configuration produced only 925 horsepower. Mitsubishi's Kinsei engine produced similar power. These engines were reliable and fuel-efficient, but they could not match the raw power of Western designs. Japanese metallurgy lagged in the specialized alloys required for high-temperature turbine components. Japanese aviation gasoline had lower octane ratings than American or British fuels, which limited compression ratios and power output. Horikoshi faced a binary choice. He could design a conventional fighter that would be outperformed by Western aircraft, or he could challenge every assumption about what a fighter had to be. The central problem was weight. Everything the Navy wanted required power, and the most powerful engine available was the Nakajima Seiki 12 radial, producing 925 horsepower. American and British fighters of the period used engines approaching 1,200 horsepower and still could not match all of the Navy's requirements. Horikoshi understood that he could not add power. He had to subtract mass. The target was a fully loaded combat weight under 2,800 kilograms. The only way to reach it was to strip away everything that did not directly contribute to the three fundamental objectives: speed, range, and maneuverability. Horikoshi's team selected a new aluminum alloy called Extra Super Duralumin, developed by Sumitomo Metal Industries. It offered 30% greater strength than conventional aircraft aluminum, which meant airframe components could be made thinner and lighter while maintaining structural integrity. The wings were designed as a single, continuous structure that passed through the fuselage rather than being attached to it. This integral wing design reduced weight and increased strength at the critical junction point where aerodynamic forces concentrated during high-G maneuvers. Every component underwent weight analysis. The wing structure used a minimal number of ribs and stringers. Skin panels were stamped to the thinnest gauge that structural analysis permitted. The landing gear was engineered with such precision that its weight dropped to 285 kilograms, roughly half what equivalent systems weighed on contemporary fighters. Even the cockpit instruments were selected for minimal mass. Horikoshi's team eliminated the radio, reasoning that fighters operating in tight formations over visual ranges did not need complex communication systems. They designed the control surfaces without hydraulic boosting, using direct cable linkages that responded to stick pressure with mechanical purity. The fuel system represented the most severe compromise. The Navy's range requirement demanded an internal capacity of 518 liters, with provisions for an external 330-liter drop tank. Fuel is heavy. 1 liter of aviation gasoline weighs 720 grams, meaning a full load added 373 kilograms to the aircraft. Protecting that fuel with self-sealing tanks and surrounding it with armor plate to shield the pilot would add another 150 to 200 kilograms. Horikoshi made the calculation that would define the Zero's strengths and haunt its combat record. He left the fuel tanks unprotected. He left the pilot unarmored. Construction of the first prototype began in January 1939 at Mitsubishi's Nagoya plant. The airframe took shape in a secured hangar where skilled craftsmen worked with templates and jigs designed to maintain tolerances within fractions of a millimeter. The Extra Super Duralumin alloy required special handling. It could not be welded, so all joints used rivets or bolts. The rivets themselves were countersunk flush with the skin to minimize drag. Each major assembly underwent stress testing before installation. The wing structure demonstrated Horikoshi's engineering philosophy. Rather than building two separate wing panels and attaching them to a central fuselage structure, the design used a continuous wing spar that passed through the fuselage as a single piece. This approach eliminated the weight of attachment fittings and distributed flight loads more evenly across the airframe. The wing's aspect ratio was relatively high, with a span of 12 meters and area of 22 square meters. High aspect ratio reduced induced drag and improved fuel efficiency during cruise flight. The landing gear presented unique challenges. Carrier operations required robust gear capable of absorbing the shock of arrested landings. But weight constraints demanded a minimal solution. Horikoshi's team designed a manually retracted system that folded backward into wells in the wing. The pilot cranked a hand wheel to raise and lower the gear, a process requiring approximately 30 seconds of sustained effort. The system saved approximately 20 kilograms compared to hydraulic alternatives. The cockpit reflected Spartan functionality. A simple control stick connected directly to control surfaces through cable linkages. Rudder pedals operated the vertical stabilizer. Throttle, mixture control, and propeller pitch lever occupied the left side panel. Flight instruments included airspeed indicator, altimeter, compass, turn and bank indicator, engine gauges showing oil pressure and temperature, fuel quantity, and manifold pressure. No radio meant no communication equipment weight. Navigation relied on compass headings and pilotage. The prototype A6M first flew on April 1, 1939, at Kagamigahara Airfield. Test pilot Katsuzo Shima advanced the throttle and felt the Nakajima Zuisei engine's 780 horsepower pull the aircraft into the air after a ground roll of just 70 meters. The landing gear retracted cleanly. Climb was extraordinary. At 3,000 meters, with the aircraft still accelerating, Shima banked into a turn and understood immediately that the Zero possessed flight characteristics unlike any fighter he had tested. The turning radius was impossibly tight. Stall speed was below 105 km per hour. Roll rate was crisp at low speeds but remained controllable. The aircraft responded to control inputs with a precision that suggested aerodynamic refinement far beyond typical military designs. The Navy's evaluation revealed an aircraft that exceeded specifications in most areas but required more power to reach the maximum speed targets. The Zuisei engine produced adequate power for combat maneuvering but insufficient thrust for high-speed dash performance. Navy test pilots noted that the aircraft's light wing loading created excellent handling at low speeds but limited terminal velocity in dives. The combination of low power and moderate structural limits meant the A6M could not effectively disengage from combat through diving speed. The Navy ordered 15 pre-production aircraft designated A6M and specified installation of the Nakajima Seiki 12 engine. The Seiki used the same basic architecture as the Zuisei but incorporated improved supercharger design and higher compression ratios. At 2,600 revolutions per minute, the Seiki 12 produced 950 horsepower at sea level and maintained 940 horsepower at 4,200 meters. This represented a 30% increase over the Zuisei. Installing the more powerful engine required airframe modifications. The Seiki had a larger diameter than the Zuisei, which necessitated redesigning the engine cowling. Horikoshi's team used this opportunity to refine the cowling's aerodynamics, incorporating more efficient cooling airflow management. The oil cooler moved from the fuselage to the underside of the cowling. Engine mounts were strengthened to handle increased vibration and torque loads. The propeller presented challenges. The Seiki's increased power required a larger diameter propeller to convert horsepower into thrust efficiently. But a larger propeller reduced ground clearance, which was already minimal given the short landing gear required for carrier operations. The solution was a 3-blade constant-speed propeller with a diameter of 3.05 meters, representing the maximum size that could fit within the available clearance envelope. The Navy tested the prototype and requested a more powerful engine. Horikoshi's team installed the Nakajima Seiki 12, producing 925 horsepower, and redesignated the aircraft A6M. Maximum speed reached 533 km per hour at 4,500 meters. Climb to 6,000 meters took 6 minutes and 50 seconds. With the external drop tank, combat radius exceeded 1,600 kilometers. Every specification had been met or exceeded. The Navy accepted the design in July 1940 and designated it the Type 0 carrier fighter, marking the year 2600 in the Japanese imperial calendar. Pilots and ground crews shortened this to Rei-sen, meaning Zero Fighter. The Americans would adopt the same name. What Horikoshi created was an aircraft optimized for a specific tactical doctrine. Japanese naval aviation theory in the late 1930s emphasized offensive operations launched from carrier groups that would strike enemy fleets before they could close to effective range. Fighters needed to escort bombers across vast Pacific distances and then engage enemy aircraft in turning combat where superior maneuverability would allow a smaller number of elite pilots to defeat larger enemy formations. The Zero's design reflected this doctrine with brutal clarity. Everything was sacrificed to achieve range and agility. Protection was considered secondary to the skills of the pilots who would fly it. The aircraft and the doctrine that shaped its design requirements represented only part of the equation. The human element, the pilots who would fly the Zero into combat, completed the system. The Imperial Japanese Navy understood that superior aircraft alone could not guarantee victory. The pilot's skill, training, physical conditioning, and psychological preparation determined whether technical advantages translated into combat success. Japan's approach to pilot training in the 1930s reflected cultural values and military philosophy that had evolved over centuries. The samurai tradition emphasized mastery through relentless practice, subordination of individual comfort to collective goals, and cultivation of fighting spirit that transcended physical limitations. These values shaped the Navy's pilot training program into one of the most demanding and selective in the world. The process began with the Youth Pilot Training Program, which accepted boys as young as 14. Candidates underwent rigorous physical examinations that assessed vision, hearing, reflexes, coordination, and cardiovascular fitness. Academic testing evaluated mathematical ability, spatial reasoning, and educational background. Psychological screening attempted to identify candidates with the mental resilience to withstand the stress of combat and the discipline to follow orders under fire. Acceptance rates ranged from 2 to 5%. Of 1,000 applicants, perhaps 20 to 50 would be selected. These chosen few entered a residential training program that lasted 3 years. The first year emphasized general education and military indoctrination. Candidates studied mathematics, physics, navigation, meteorology, and military history. They underwent physical conditioning that included long-distance running, swimming, gymnastics, and martial arts. They learned naval customs, ranks, and protocols. The second year introduced aviation fundamentals. Candidates learned aircraft systems, engine operations, and flight theory. They practiced in procedural trainers that simulated cockpit layouts and control responses. They studied aircraft recognition, learning to identify friendly and enemy aircraft types at various angles and distances. They practiced navigation using charts and dead reckoning. They learned radio procedures and Morse code. The third year brought actual flight training. Candidates progressed through a sequence of aircraft types, beginning with basic trainers with forgiving handling characteristics and advancing to increasingly demanding machines. Initial instruction covered basic flight maneuvers, takeoffs, landings, climbs, descents, turns, and stalls. Candidates learned to recover from spins and unusual attitudes. They practiced forced landing procedures and emergency responses. Advanced training introduced aerobatics, formation flying, and instrument flight. Candidates learned loops, rolls, spins, and more complex maneuvers like the Immelmann turn and split S. They practiced flying in close formation, maintaining position relative to lead aircraft through turns, climbs, and descents. They developed the situational awareness required to track multiple aircraft while maintaining formation discipline. They learned to fly by reference to instruments alone, navigating in clouds or darkness without visual reference to the horizon. Gunnery training came late in the program. Candidates learned to operate machine guns, understanding ballistics, bullet trajectory, and deflection angles. They practiced shooting at towed targets, developing the ability to estimate range and lead angle while maneuvering in 3 dimensions. They learned the difference between fixed gun and turret gun operations. They studied ammunition types and their effects on different target materials. Those pilots represented Japan's second advantage. The Imperial Japanese Navy's flight training program in the late 1930s was among the most rigorous and selective in the world. Candidate selection began at age 14 or 15, with applicants undergoing physical examinations, academic testing, and psychological evaluation. Those accepted entered a 3-year preparatory course that combined general education with basic military training. From this group, a small percentage qualified for pilot training, which lasted an additional 2 years. The curriculum included 300 to 700 flight hours depending on the track, covering basic flight, aerobatics, formation flying, navigation, gunnery, and combat tactics. By the time a pilot reached operational status, he typically had accumulated more than 500 flight hours and spent several additional months training with his squadron. Many of the pilots assigned to carrier air groups in 1940 had combat experience from operations over China, where Japanese naval aviation had been fighting since 1937. They understood air combat not as theory but as lived experience involving altitude management, energy tactics, deflection shooting, and the psychological pressure of being shot at while trying to maintain formation discipline. When the first operational Zero units deployed to China in August 1940, these pilots took an aircraft that matched their skills. The Zero made its combat debut on August 19, 1940, when 12 A6M2s escorted 54 G3M2 bombers on a raid against Chongqing, the wartime capital of the Republic of China. Chinese fighters rose to intercept. What followed shocked both sides. The Zeros engaged 34 Chinese aircraft, including IA-15 and IA-16 fighters supplied by the Soviet Union. In the span of 12 minutes, Japanese pilots claimed 27 kills. Not a single Zero was lost. This pattern repeated through the autumn of 1940. Chinese pilots found themselves unable to engage the Zero on any terms that offered survival. The Japanese fighters operated at altitudes previously considered the domain of interceptors. They maneuvered with a fluidity that made conventional pursuit curves irrelevant. Their range allowed them to appear anywhere, escort bombers to targets deep in Chinese airspace and still return to base with fuel reserves. In the first months of combat operations over China, Zeros destroyed more than 150 Chinese aircraft while suffering fewer than 10 losses. The reports from China painted a picture of air combat that American and British intelligence officers found difficult to credit. Chinese pilots described being attacked by formations of Japanese fighters that appeared suddenly at high altitude, dived through the Chinese formations with devastating effect, and then climbed back to altitude faster than the Chinese aircraft could pursue. The Japanese fighters could outturn anything the Chinese flew. They could sustain prolonged engagements without running low on fuel. They carried surprisingly heavy armament for fighters, with two 20mm cannons supplementing machine guns. Specific performance figures seemed implausible. Maximum speed reportedly exceeded 330 miles per hour. Service ceiling approached 33,000 feet. Rate of climb reached 3,000 feet per minute. Combat radius exceeded 700 miles. These specifications individually were achievable, but American analysts believed that combining all of them in a single airframe required engine power that Japan did not possess. The Nakajima Seiki engine was known to produce less than 1,000 horsepower. American fighters with 1,200 horsepower engines could not match all of these specifications. The skepticism reflected systemic biases that pervaded Western military analysis. Intelligence assessments of Japanese capabilities consistently underestimated Japanese engineering and manufacturing competence. These underestimates stemmed partly from racial prejudice and partly from assumptions about industrial development. Japan had industrialized rapidly in the late 19th and early 20th centuries, but Western observers assumed that Japanese industry copied Western technology rather than innovating independently. The idea that Japanese engineers could develop original solutions to aeronautical problems contradicted prevailing assumptions. Claire Chennault represented a notable exception. Chennault had retired from the U.S. Army Air Corps in 1937 and accepted a position as aviation advisor to the Chinese nationalist government. He organized the Chinese Air Force's training programs and developed defensive tactics against Japanese air raids. By 1940, he had spent 3 years observing Japanese aviation operations firsthand. His reports emphasized that the Japanese Zero fighter represented a genuine technological achievement that posed serious threats to Allied aircraft. Chennault's cables to Washington described specific tactical characteristics. The Zero could execute sustained turns at speeds where American fighters would stall. It could climb at steep angles that American fighters could not match. It could operate at combat altitudes while carrying significant fuel loads. Chennault emphasized that pilots encountering Zeros should never attempt turning combat at low speeds. He recommended using altitude advantage to attack with high-speed diving passes, firing during the dive, and using superior diving speed to disengage before the Zero could respond. Intelligence reports from China reached American and British air staffs in late 1940 and early 1941. The reports described an aircraft with performance characteristics that seemed impossible. One assessment noted a top speed exceeding 320 miles per hour, maneuverability superior to any known fighter, and operational range approaching 2,000 miles. Claire Chennault, the American aviation advisor to the Chinese nationalist forces, submitted detailed analyses based on direct observation and pilot debriefs. He emphasized that the Zero could not be engaged in turning combat and recommended strict hit-and-run tactics using superior altitude and speed. American intelligence analysts read these reports with skepticism. The consensus view held that Japanese industrial capacity could not produce engines powerful enough to match Western designs. Japanese aircraft were assumed to be copies of European models, assembled with inferior materials and craftsmanship. The idea that Japan had developed a world-class fighter seemed implausible given the racist assumptions that pervaded Western military thinking. The reports from China were filed and largely ignored. The 6 carriers of the Kido Butai Strike Force departed Hitokapu Bay in the Kurile Islands on November 26, 1941, following a route across the North Pacific chosen for minimal merchant shipping traffic. The task force maintained radio silence and refueled from accompanying tankers while crossing 3,500 miles of ocean. Aboard the carriers Akagi, Kaga, Soryu, Hiryu, Shokaku, and Zuikaku, pilots conducted final briefings and reviewed target photographs. Zero pilots studied maps of Oahu showing airfield locations, anti-aircraft battery positions, and expected fighter patrol patterns. Commander Mitsu Fukaida led the first attack wave, launched at 0600 hours on December 7 from a position 230 miles north of Oahu. The formation included 49 high-level bombers armed with armor-piercing bombs converted from battleship shells, 40 torpedo bombers carrying Type 91 aerial torpedoes, 51 dive bombers with 250 kg general-purpose bombs, and 43 Zeros assigned to fighter escort and airfield suppression roles. The formation flew south in radio silence, navigating by compass heading and dead reckoning. The Zeros operating in the Pearl Harbor attack flew A6M Model 21 variant with the wing folding mechanism that allowed more aircraft to fit in carrier hangars. Each Zero carried 120 rounds of 20mm ammunition for each cannon and 680 rounds for each 7.7mm machine gun. Maximum internal fuel load was 518 liters, providing approximately 3 hours of flight time at cruise power settings. Pilots carried charts showing the return course to the carriers and emergency landing procedures if damage or fuel shortage prevented return. At 0755 hours, Fukaida transmitted the code Tora, 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 indicating surprise had been achieved. The first wave struck the Pacific Fleet's battleships moored along Ford Island. Torpedo bombers attacked from the west, releasing torpedoes that ran shallow through Pearl Harbor's 40-foot depths. High-altitude bombers attacked from 10,000 feet, dropping armor-piercing bombs that penetrated battleship decks. Dive bombers attacked cruisers and destroyers. The Zeros split into sections assigned to attack different airfields. The attack on Pearl Harbor on December 7, 1941, shattered these assumptions with the precision of armor-piercing bombs. 6 Japanese carriers launched 183 aircraft in the first wave, including 43 Zeros assigned to fighter escort and airfield suppression. The Zeros strafed airfields at Wheeler Field, Hickam Field, and Kaneohe Naval Air Station, destroying aircraft parked in neat rows on the tarmac. When American pilots managed to get airborne, the few encounters that occurred demonstrated the Zero's superiority in vertical and horizontal maneuvering. Second Lieutenant George Welsh and Second Lieutenant Kenneth Taylor, flying P-40 Warhawks from Haleywa Field, engaged the Japanese formation and claimed several kills, but they fought using slashing diving attacks rather than turning combat, tactics that preserved their lives through speed and altitude management. The second wave included 36 Zeros. They patrolled over the target area, engaging any American aircraft that managed to get airborne and suppressing anti-aircraft positions. The Zeros operated with complete tactical flexibility, attacking ground targets, escorting bombers, and fighting in the vertical and horizontal planes with equal facility. By the time the Japanese formation withdrew, the Zeros had destroyed more than 180 American aircraft on the ground and in the air, including fighters, bombers, and patrol aircraft. Zero losses numbered fewer than 10, mostly to anti-aircraft fire rather than aerial combat. The tactical success of the Pearl Harbor raid derived from multiple factors working in combination. Surprise eliminated organized resistance during the crucial first minutes. The concentration of targets in a confined area allowed weapons to be employed with maximum efficiency. Japanese aircrew training and planning enabled precise coordination of multiple attack elements arriving from different directions at nearly simultaneous times. And the Zero provided the qualitative advantage that allowed relatively small numbers of fighters to suppress defensive reactions. American losses included 8 battleships sunk or damaged, 3 cruisers damaged, 3 destroyers damaged, and 188 aircraft destroyed or damaged on the ground. Japanese losses numbered 29 aircraft, including 9 Zeros, 5 torpedo bombers, and 15 dive bombers. The loss ratio of more than 6-to-1 favored Japan despite American advantages in defensive positions and anti-aircraft firepower. The psychological impact exceeded the material damage. The attack demonstrated that American forces were vulnerable to sudden, devastating strikes launched from unexpected directions. The Zero's performance shocked American pilots who managed to engage them. Lieutenant John Thatch, who witnessed the attack while stationed at Ford Island, noted in his report that Japanese fighters demonstrated maneuverability and speed exceeding American intelligence estimates. Lieutenant Welsh and Lieutenant Taylor, who shot down multiple Japanese aircraft while flying P-40s, emphasized in their debriefs that they survived only by avoiding turning combat and using diving speed to disengage. The pattern established at Pearl Harbor repeated across the Pacific in the opening months of the war. On December 8, 1941, Zeros based in Taiwan escorted bombers attacking American airfields in the Philippines. At Clark Field and Iber Field, they caught American B-17 bombers and P-40 fighters on the ground, destroying dozens before effective resistance could be organized. When American pilots engaged, they discovered the same brutal reality their counterparts at Pearl Harbor had faced. The Zero turned inside any American fighter. It climbed faster, accelerated more quickly at low speeds, and maintained energy in sustained turns that would force American aircraft to disengage or stall. The Japanese advance rolled south through the Philippines, Malaya, the Dutch East Indies, and New Guinea. Everywhere the carrier groups and land-based air units went, Zeros established air superiority within days. They escorted bombers attacking Allied airfields and naval installations. They swept ahead of invasion forces, eliminating air opposition before ground troops landed. They protected Japanese shipping from Allied air attacks. The tactical flexibility of the Zero made it effective in every role the Japanese assigned. At the Battle of the Java Sea on February 27, 1942, Zeros provided top cover for Japanese naval forces engaging an Allied fleet. They shot down Dutch and British aircraft attempting to attack Japanese transports. In Burma, Zeros engaged British Hurricane fighters and American volunteer Group P-40s flown by Chennault's pilots. The average survived by refusing to engage in turning combat, using diving attacks and rapid disengagement, but losses mounted. In New Guinea, Zeros operating from Rabaul and Lae dominated the skies over Port Moresby, shooting down Australian and American aircraft. Attempting to defend the base. The opening months of 1942 saw Japanese forces advance across Southeast Asia and the Southwest Pacific with a speed that stunned Allied commanders. Zeros operating from carriers and captured airfields established air superiority over each objective area before ground forces landed. In Malaya, Zeros based in Thailand escorted bombers attacking British airfields near Singapore. They shot down Brewster Buffalo fighters defending the base and destroyed aircraft on the ground. In the Dutch East Indies, Zeros operating from bases in Borneo and Celebes swept Allied aircraft from the skies, enabling Japanese forces to capture oil facilities and ports. In the Philippines, Zeros flying from bases in Taiwan and later from captured fields on Luzon dominated the air, supporting the siege of Bataan and Corregidor. The tactical pattern was consistent. Japanese reconnaissance aircraft located Allied airfields and naval bases. Bomber formations escorted by Zeros struck during daylight hours, attacking parked aircraft, fuel storage facilities, and anti-aircraft positions. Allied fighters scrambling to intercept faced numerical disadvantages and performance disparities. The Zeros used altitude advantage to position for attacks, diving through Allied formations with superior speed and then climbing back to altitude using better power-to-weight ratios. Allied fighters attempting to pursue found themselves outrun in climbs and unable to follow the Zeros through sustained turns. American carrier pilots faced the Zero for the first time in sustained combat during raids on Japanese bases in the Marshall Islands and at Rabaul in February 1942. Fighting Squadron 3, flying F-4F Wildcat fighters from the carrier USS Lexington, engaged Zeros in combat that demonstrated both the Wildcat's limitations and its potential. The Wildcat was slower than the Zero, climbed less effectively, and could not match its turning performance. But it was rugged. The F-4F featured armor protection for the pilot, self-sealing fuel tanks, and a robust radial engine that could absorb significant battle damage. Its 6.50 caliber machine guns delivered devastating firepower at close range. Lieutenant Edward Butch the Hare discovered the key to surviving Zero attacks during a combat mission on February 20, 1942. When 9 Japanese G-4M bombers attacked the Lexington, a Hare and his wingman intercepted. A Hare made repeated head-on passes against the bomber formation, expending only 60 rounds of ammunition per attack and shooting down 5 bombers in less than 4 minutes. He survived by using high-speed passes that denied Zero escorts the opportunity to engage in turning combat. The tactic demonstrated that American pilots could fight the Zero if they avoided its strengths and exploited its weaknesses. Lieutenant Commander John Thatch systematically analyzed Zero combat characteristics and developed tactical responses during the spring of 1942. Thatch commanded Fighting Squadron 3 aboard the USS Yorktown and spent hours studying combat reports and intelligence assessments. He recognized that individual American fighters could not defeat Zeros in one-on-one combat. The solution was mutual support through coordinated maneuvers. Thatch devised a defensive tactic he called the beam defense maneuver, which pilots and historians would later call the Thatch weave. The tactic required 2 fighters flying parallel courses about 200 feet apart. When a Zero attacked one aircraft, both fighters turned toward each other. The Zero pilot, committed to his attack on the first aircraft, found himself approaching head-on toward the second American fighter, which could bring guns to bear in a high-deflection shot. If the Zero tried to follow the first aircraft through the turn, it would pass in front of the second American fighter, again presenting a firing opportunity. If the Zero disengaged, the American fighters could re-establish their formation and prepare for the next attack. Thatch first employed the weave in combat at the Battle of Midway on June 4, 1942. The Yorktown's air group launched attacks against the Japanese carrier fleet, and Fighting Squadron 3 provided escort for torpedo bombers attacking the carriers. Zeros from the Japanese Combat Air Patrol intercepted the American formation. Thatch and his wingmen engaged using the weave pattern. The defensive maneuver worked exactly as designed. The Zeros could not complete their attacks without exposing themselves to defensive fire. Thatch's division shot down 3 Zeros and damaged several others while suffering no losses. The tactic spread through the U.S. Navy's fighter squadrons in the following months and became standard doctrine. But tactical innovations alone could not change the fact that in June 1942, the Zero remained the superior aircraft in most performance categories. At Midway, Marine Corps fighters flying obsolete F-2A Buffalo and F-4F Wildcat aircraft attempted to defend the atoll against Japanese air attacks. Marine Fighter Squadron 221 engaged Zero escorts and suffered catastrophic losses. Of the 25 Marine fighters that engaged, 15 were shot down and 7 others were so badly damaged they never flew again. The Zeros and Japanese bomber escorts destroyed them through superior speed, climb rate, and maneuverability. American pilots and engineers in mid-1942 understood that the Zero could be defeated through specific tactical approaches, but implementation required aircraft capable of executing those tactics. The F-4F Wildcat could fight Zeros using defensive weaves and high-speed hit-and-run attacks, but its performance margins were thin. A pilot error or mechanical problem could prove fatal. What American aviation needed was detailed technical intelligence about the Zero's specific capabilities and limitations. Combat reports provided qualitative descriptions: turns tight, climbs fast, poor at high speeds, but engineers needed quantitative data. How tight could the Zero turn at specific airspeeds? What was its maximum roll rate at 250 miles per hour versus 350 miles per hour? At what speed did control forces become prohibitive? What were the structural limits for diving speed and G-loading? These questions could only be answered by testing an actual Zero under controlled conditions. Japanese security procedures made capturing an intact Zero nearly impossible. Damaged Zeros ditching at sea sank quickly due to lack of flotation provisions. Zeros shot down over land typically burned, destroying critical components. Japanese pilots facing certain capture were instructed to destroy their aircraft and kill themselves rather than allowing the enemy to examine their equipment. The turning point came not from tactical innovation but from fortune and intelligence work. On June 4, 1942, the same day as the Battle of Midway, a Zero launched from the carrier Ryujo participated in the Japanese attack on Dutch Harbor, Alaska. The aircraft, flown by Petty Officer First Class Tadayoshi Koga, suffered damage during the attack. Oil from a severed return line sprayed across the windscreen, partially blinding Koga. He attempted to reach the emergency landing site on Akatan Island, a small landmass 45 miles from Dutch Harbor designated as an emergency recovery area. Koga approached what appeared to be a grassy field suitable for a wheels-down landing. The field was actually a marsh covered with dense vegetation. When the Zero's wheels touched down, they caught in the soft ground and the aircraft flipped inverted. Koga, who had not fastened his seatbelt in anticipation of evacuating quickly after landing, struck his head on the instrument panel and died instantly. The Zero, virtually intact, settled into the marsh upside down. The Zero remained undiscovered for more than a month. Akatan Island, located in the Aleutian chain, was remote, fog-bound, and rarely visited. The vegetation that had trapped Koga's aircraft also concealed it from casual observation. But American forces were conducting systematic searches of the Aleutian Islands following the Japanese attacks on Dutch Harbor. These searches aimed to locate potential Japanese landing sites and establish early warning positions. On July 10, 1942, a U.S. Navy PBY Catalina flying boat conducting a reconnaissance patrol over Akatan Island spotted what appeared to be an aircraft partially concealed in vegetation near the coastline. The pilot circled for a closer look and identified Japanese markings. A subsequent low-level pass revealed the aircraft was remarkably intact, lying inverted but with no obvious major damage. The pilot marked the location and radioed the discovery to his base. A recovery team deployed from Dutch Harbor 3 days later. Navy Lieutenant William Thies led the operation, bringing mechanics, equipment, and a barge to transport the recovered aircraft. The team hiked inland from the beach to the crash site and began assessment. The Zero had flipped when its landing gear sank into the marsh, but the airframe had not buckled. The wings were intact. The fuselage showed no major structural damage. The engine appeared undamaged. Koga's body remained in the cockpit, and the team buried him near the crash site with military honors. Recovery required 3 weeks of work in difficult conditions. The team constructed a wooden ramp to roll the Zero onto its wheels after righting it. They disassembled the outer wing panels to reduce width for transport. They drained fluids and removed the engine to reduce weight. Each component was catalogued and photographed. The disassembled Zero was loaded onto the barge, transported to Dutch Harbor, and then loaded aboard a ship bound for the United States. A U.S. Navy patrol discovered the Zero 5 weeks later on July 10, 1942. The aircraft had been preserved by the cold water and peat of the marsh. A recovery team from the Navy's Fleet Air Base at Dutch Harbor examined the site and determined the Zero could be salvaged. They carefully excavated the aircraft, disassembled major components, and transported it to Dutch Harbor. From there, it was shipped to Naval Air Station North Island in San Diego, California. The Zero arrived at Naval Air Station North Island in San Diego in late August 1942. The crated components were transported to a secured hangar where a team of engineers and mechanics began restoration under the supervision of Commander Frederick Trapnell, one of the Navy's most experienced test pilots. Trapnell had evaluated virtually every fighter type in American service and had extensive combat experience. He understood what information combat pilots needed to fight the Zero effectively. Restoration took 3 weeks. The engine required cleaning and inspection but proved mechanically sound. The Nakajima Seiki 12's 14 cylinders showed normal wear patterns. Valve timing and ignition systems functioned correctly. The carburetor and fuel system required cleaning to remove sediment from storage. The propeller hub and blades were intact. Hydraulic lines needed replacement due to deterioration from exposure. The airframe required minimal structural work. Several wing ribs had minor cracks that were repaired with patches. Control cables were inspected and several were replaced as precautions. The landing gear mechanism was disassembled, cleaned, and lubricated. Flight control surfaces were examined for proper balance and freedom of movement. All instruments were removed, tested, and reinstalled or replaced with American equivalents. The most revealing aspect of the restoration was what the team learned about the Zero's construction. The skin panels were extraordinarily thin, averaging 1 mm in thickness over most of the airframe. By comparison, American fighters like the F-4F Wildcat used skin panels averaging 1.5 to 2 mm. The thinner panels saved weight but provided minimal protection against battle damage. A single .50 caliber bullet striking the fuselage would penetrate both sides with energy to spare. The fuel tanks occupied the fuselage section directly behind the cockpit and the inboard wing sections. The tanks were simple aluminum structures with no self-sealing liners or fire suppression systems. Testing showed that a single incendiary bullet striking a fuel tank would ignite the fuel within seconds. The fire would spread rapidly through the tank structure, producing flames that would engulf the cockpit in less than 30 seconds. The pilot had no armor protection from behind. The windscreen was standard glass with no armor layer. The recovery of an intact, flyable Zero represented an intelligence breakthrough of extraordinary value. American engineers and test pilots had been trying to understand the Zero's capabilities based on fragmentary evidence, combat reports, and intelligence assessments. Now they had the actual aircraft. A team led by Commander Frederick Trapnell began restoration work in August 1942. The Zero had suffered minimal damage in the crash. The engine was intact. Control surfaces were undamaged. The airframe required only minor repairs. The test program developed by Commander Trapnell aimed to quantify every aspect of the Zero's performance envelope. The Navy needed specific data points that could be incorporated into tactical manuals and training programs. Combat pilots needed to know precisely what their aircraft could and could not do relative to the Zero at various speeds, altitudes, and load conditions. Engineers developing new fighters needed performance targets that would ensure American aircraft could exploit Zero weaknesses. The test plan included evaluation of maximum speed at various altitudes, rate of climb from sea level to service ceiling, acceleration from cruise to maximum speed, deceleration characteristics, turning performance at different speeds and altitudes, roll rate at different airspeeds, control force measurements, stall characteristics, and structural limits. Additional testing would examine combat maneuvers including loops, split-S, Immelmann turns, and defensive brakes. On September 20, 1942, Lieutenant Commander Edward Sanders took the captured Zero up for its first test flight from North Island. Sanders was an experienced test pilot familiar with virtually every fighter type in American service. He climbed to altitude, accelerated to cruise speed, and began systematic evaluation of the Zero's handling characteristics. What he discovered matched and exceeded the reports from China and combat operations. The Zero's rate of roll at speeds below 200 miles per hour was exceptional. Ailerons responded crisply with minimal stick force. The aircraft snapped into and out of rolls with precision that American fighters could not match. Turn performance was extraordinary. At 200 miles per hour indicated airspeed, the Zero could sustain a turn radius of approximately 630 feet. The F4F Wildcat at the same speed required nearly 850 feet. The F6F Hellcat, then in development, would require approximately 750 feet. In a sustained turn at combat speeds, the Zero could complete a full circle in less time than any American fighter could execute 3/4 of a circle. Climb rate at low and medium altitudes exceeded American fighters by substantial margins. From sea level to 10,000 feet, the Zero climbed faster than the Wildcat by nearly 1,000 feet per minute. Rate of climb remained strong up to 20,000 feet, where the Nakajima Seiki supercharger maintained power output. Sanders conducted 24 test flights over 4 weeks, systematically exploring the Zero's flight envelope. Each flight focused on specific test points with instrumentation recording airspeed, altitude, engine parameters, and control positions. Engineers on the ground photographed the aircraft during maneuvers to document control surface deflections. Some flights included chase aircraft filming the Zero performing tactical maneuvers. Maximum level speed tests were conducted at various altitudes. At sea level, the Zero reached 287 miles per hour. At 10,000 feet, speed increased to 316 miles per hour. At 15,000 feet, where the Seiki engine supercharger maintained manifold pressure most efficiently, maximum speed peaked at 331 miles per hour. Above 18,000 feet, speed declined gradually as air density decreased and engine power dropped. At 30,000 feet, maximum speed was approximately 295 miles per hour. Climb performance testing showed exceptional results at low and medium altitudes. From sea level, the Zero climbed at 3,100 feet per minute in the first 1,000 feet. Rate of climb remained above 2,500 feet per minute through 10,000 feet. At 15,000 feet, climb rate was still 2,000 feet per minute. Time from sea level to 20,000 feet was 7 minutes and 30 seconds. By comparison, the F4F Wildcat required 10 minutes to reach 20,000 feet, and the F6F Hellcat, then entering service, required 9 minutes. Turning performance tests required careful technique to avoid exceeding the Zero structural limits. Sanders established a level turn at 15,000 feet, maintaining 230 miles per hour indicated airspeed, and pulled back on the stick until buffeting indicated approaching stall. The Zero maintained a sustained turn at this condition with a radius of approximately 640 feet, completing a full circle in approximately 17 seconds. The F4F Wildcat at the same altitude and airspeed required approximately 870 feet radius and 23 seconds to complete a circle. The Zero's turning advantage was even more pronounced at lower speeds. At 180 miles per hour, the Zero could sustain turns with less than 600-foot radius, while the Wildcat would stall attempting similar turn rates. Roll rate testing revealed the Zero's most significant weakness. Sanders conducted a series of aileron rolls at different airspeeds, measuring the time required to complete a 360-degree roll. At 150 miles per hour, the Zero rolled in approximately 2 seconds, comparable to American fighters. At 200 miles per hour, roll time increased to approximately 3 seconds. At 250 miles per hour, the Zero required more than 4 seconds to complete a roll, and control forces were heavy enough that sustained rolling combat was exhausting. At 300 miles per hour, roll rate decreased further and control forces became prohibitive. At speeds above 350 miles per hour, the ailerons were essentially locked, and rolling maneuvers were impossible. But Sanders also identified critical weaknesses. Above 250 miles per hour, control forces increased dramatically. The ailerons, which responded so crisply at low speed, became increasingly heavy as speed increased. At 300 miles per hour, rolling the Zero required substantial physical strength. At speeds above 350 miles per hour, the ailerons were nearly immovable. This meant the Zero could not maneuver effectively in high-speed combat. American fighters with higher wing loading and hydraulically boosted controls could outroll the Zero at high speeds and could execute diving attacks that the Zero could not counter with rolling scissors or other high-speed defensive maneuvers. Sanders also confirmed the Zero's vulnerability to battle damage. The fuel tanks were unprotected. A single incendiary round striking a fuel tank would likely ignite the fuel, causing catastrophic fire. The pilot sat behind an unarmored windscreen with no armor plate protecting his back or head. Control cables ran exposed along the fuselage sides. Hydraulic lines were similarly vulnerable. The aircraft could absorb very little battle damage and remain flyable. The Navy distributed detailed reports on the Zero's characteristics to all fighter squadrons. Pilots learned that the Zero could be defeated through specific tactical approaches. Never attempt to turn with a Zero at low speeds. Never engage in sustained horizontal maneuvering. Use altitude advantage to initiate attacks. Make a single high-speed pass, firing during the dive, and disengage before the Zero can respond. Use superior diving speed to extend away from pursuing Zeros. If caught at low speed, use the thatch weave or other mutual support tactics. Exploit the Zero's high-speed handling limitations by forcing combat at speeds above 300 miles per hour. The Navy compiled Sanders' test data into a classified technical report designated TAIC Report No. 8, issued in October 1942. The report included performance charts, tactical recommendations, and engineering analysis. Copies were distributed to carrier air groups, training commands, and aircraft manufacturers. The information transformed American understanding of the Zero from qualitative impressions to quantitative knowledge. The tactical section of the report emphasized specific engagement strategies. Never attempt to dogfight a Zero at speeds below 250 miles per hour. The Zero will outturn any American fighter at these speeds. Use diving attacks from altitude, accelerating to speeds above 300 miles per hour before engaging. Fire during the dive and continue past the target without attempting to turn. Use superior diving speed to extend away from pursuing Zeros. If surprised at low altitude, use the thatch weave or other mutual support maneuvers. Exploit the Zero's poor high-speed handling by forcing combat at speeds above 300 miles per hour. Use rolling scissors maneuvers at high speed, where American fighters' superior roll rates provide decisive advantages. The report also noted that the Zero's light structure meant it was vulnerable to damage from even light anti-aircraft fire. A single .50 caliber hit to the fuel tanks would likely result in catastrophic fire. The lack of pilot armor meant that head-on attacks were particularly effective, as the pilot had no protection from frontal fire. The report recommended that bomber gunners concentrate fire on Zeros when possible, as even light damage could force them to break off attacks. Training commands incorporated the Zero's characteristics into fighter pilot curricula. Pilots practicing against each other learned to simulate Zero tactics by maintaining lower speeds and tighter turns. They practiced counter-tactics using speed and altitude management. They rehearsed the thatch weave until it became instinctive. They practiced deflection shooting for head-on passes. They learned energy management principles that emphasized building and maintaining speed advantages. These tactical lessons arrived at precisely the moment American industry was delivering new aircraft designed to exploit the Zero's weaknesses. Grumman Aircraft Engineering Corporation had been studying the Zero problem since late 1941. The company's engineers had access to combat reports from Pearl Harbor and early carrier engagements. They understood that the F-4F Wildcat, while a rugged and reliable fighter, lacked the performance margins needed to dominate Zeros in combat. Grumman began design work on the Wildcat's replacement in 1941, before detailed information about the Zero became available. The preliminary design emphasized evolutionary improvements, more power, better climb rate, higher speed, and increased firepower. The discovery and testing of the acrobat Zero in mid-1942 arrived while the F-6F Hellcat was still in early flight test. Grumman engineers received copies of TAIC Report No. 8 and incorporated its findings into the development program. While the Hellcat's basic design was too far advanced to change fundamentally, detailed modifications enhanced its capabilities against the Zero. The F-6F Hellcat, developed by Grumman Aircraft Engineering Corporation, flew for the first time on June 26, 1942. The Hellcat was designed around a 2,000 horsepower Pratt & Whitney R2800 double Wasp radial engine, more than twice the power of the Zero's Nakajima Seiki. This power gave the Hellcat a maximum speed of 391 miles per hour at 17,300 feet, substantially faster than the Zero's 331 miles per hour. The production F6F3 variant that entered fleet service in early 1943 represented a fundamentally different design philosophy than the Zero. Where the Zero optimized maneuverability and range through extreme weight reduction, the Hellcat optimized combat effectiveness through brute force and survivability. The Pratt & Whitney R2800 double Wasp engine produced 2,000 horsepower, more than twice the Zero's power output. This massive engine weighed 2,360 pounds installed, nearly 40% of the Zero's total empty weight. The Hellcat weighed 12,598 pounds fully loaded, nearly twice the Zero's 6,164 pounds. That weight came from armor protection for the pilot, self-sealing fuel tanks, a robust airframe designed to survive battle damage, and heavy armament consisting of 6.50 caliber machine guns with 2,400 rounds of ammunition. The Hellcat could not turn with the Zero. It could not climb with the Zero at low altitudes. But it could outrun the Zero at any altitude. It could outdive the Zero. It could absorb battle damage that would destroy a Zero. And it was arriving in squadron strength by early 1943. The F-4U Corsair, developed by Vought Aircraft, represented an even more significant threat. Powered by the same ARD-2800 engine tuned for higher performance, the Corsair achieved a maximum speed of 417 miles per hour, making it one of the fastest fighters of the war. Its rate of climb approached 4,000 feet per minute. Like the Hellcat, it featured armor protection and self-sealing tanks. Its armament consisted of 6.50 caliber machine guns, later upgraded to 20mm cannons in some variants. The first major engagement between Hellcats and Zeros occurred during the invasion of Tarawa in November 1943. Navy Fighter Squadron VF-5, equipped with F-6F3 Hellcats and embarked on the carrier USS Yorktown, flew combat air patrols and escort missions supporting the landing operations. On November 23, 1943, a formation of Zeros from Rabaul attacked the American fleet. VF-5 intercepted at 18,000 feet. The engagement demonstrated the Hellcat's advantages. American pilots maintained altitude discipline, refusing to descend to the Zero's preferred combat altitude. When Zeros climbed to engage, Hellcat pilots used superior power to accelerate away, then reversed and attacked from advantageous positions. The Zeros could still outturn the Hellcats at low speeds, but Hellcat pilots simply refused to fight at low speeds. They used diving attacks, fired during high-speed passes, and extended away using superior speed. When Zeros pursued, Hellcat pilots used rolling maneuvers at high speed, exploiting the Zero's poor high-speed handling. VF-5 claimed 11 Zeros destroyed for no losses. This pattern repeated through 1943 and early 1944 as more carrier air groups transitioned to Hellcats. American pilots, flying aircraft with performance advantages and armed with tactical knowledge from the acrobat Zero's testing, increasingly dominated Zero formations. The kill ratio shifted dramatically. At midway in June 1942, American fighters claimed approximately 1.5 kills for each loss. By mid-1943, Hellcat pilots were achieving ratios exceeding 5-1. By mid-1944, the ratio approached 13-1. Japanese engineers recognized the Zero's increasing obsolescence. They attempted to develop improved versions with more powerful engines, better armament, and some protection for the pilot. The A6M model incorporated the Seiki 21 engine with a two-stage supercharger, improving high-altitude performance. The A6M5 model featured a more powerful engine, heavier wing structure, and increased diving speed limits. The A6M6 added self-sealing fuel tanks and limited pilot armor. But each improvement added weight, which reduced the maneuverability and range that made the Zero effective. The modifications were incremental while American aircraft represented generational leaps. The fundamental problem was that Japan lacked the industrial capacity to design, test, and mass-produce an entirely new fighter while simultaneously fighting a war across the Pacific. Mitsubishi developed the A7M Repu as the Zero's replacement, but the aircraft did not fly until 1944 and never entered production. Kawanishi developed the N1K Shiden land-based interceptor, which showed promise, but production numbers remained limited. By 1944, Japanese naval aviation was forced to rely on variants of the Zero designed in 1937 to face American fighters designed in 1942 and 1943. The strategic implications became clear during the Battle of the Philippine Sea on June 19 to 20, 1944. The Japanese mobile fleet launched massive air strikes against American carrier task forces in what Japanese planners called Operation Ago. The Japanese committed approximately 450 carrier-based aircraft to the attack, including more than 200 Zeros. The Americans deployed approximately 450 F-6F Hellcats. The resulting engagement became known as the Great Marianas Turkey Shoot. American pilots, flying aircraft with superior speed, firepower, and protection, combined with tactical discipline developed over 2 years of combat, systematically destroyed the Japanese formations. American fighters controlled altitude, using radar direction to position themselves above incoming Japanese attacks. They made high-speed diving passes, engaging with their .50 caliber machine guns at ranges where the Zeros could not effectively respond. When Zeros attempted to turn into the attacks, American pilots used their superior speed to disengage, climb, and set up another pass. The slaughter was comprehensive. By the end of June 19, the Japanese had lost approximately 330 aircraft and pilots. American losses numbered fewer than 30. The kill ratio exceeded 10-1, the inverse of the ratios Japanese pilots achieved over China in 1940. The Japanese mobile fleet's carrier air groups were effectively annihilated. Many of the lost pilots represented the final cadre of experienced aviators who had trained before the war. Their replacement pilots, rushed through abbreviated training programs, lacked the skill to exploit even the Zero's remaining advantages. The final chapter of the Zero's combat service came during the kamikaze campaigns of 1944 and 1945. As Japan's strategic position collapsed and pilot quality declined, Japanese commanders adopted suicide tactics. Zeros, stripped of armor and loaded with 250-kilogram bombs, flew one-way missions targeting American ships. The tactic reflected the Zero's original design philosophy taken to its logical extreme. Range and maneuverability supported the approach to the target. Protection was irrelevant if the pilot did not intend to return. The kamikaze campaign inflicted significant casualties on American naval forces, sinking or damaging dozens of ships and killing thousands of sailors. But it consumed Japan's remaining pilots and aircraft in a purely attritional exchange that Japan could not sustain. By August 1945, when the war ended, the Imperial Japanese Navy's air service had effectively ceased to exist. The Zero's dominance lasted approximately 18 months, from December 1941 through mid-1943. During that period, it was arguably the most effective carrier-based fighter in the world. It enabled Japanese naval aviation to achieve air superiority across the Pacific and Indian Oceans, supporting amphibious operations and protecting naval forces. The Zero's combat debut shattered Western assumptions about Japanese technological capabilities and forced Allied air forces to develop new tactics and aircraft to counter it. But the Zero's design embodied trade-offs that proved fatal when the tactical and technological environment shifted. The extreme focus on range and maneuverability, purchased through elimination of protection, created an aircraft that could dominate inexperienced opponents flying inferior aircraft but could not survive against skilled pilots flying fighters designed to exploit its weaknesses. The Zero's lack of development potential meant that incremental improvements could not keep pace with American fighters that represented entirely new design philosophies. the strategic implications extended beyond tactical aviation. The Zero's early success encouraged Japanese military planners to believe that qualitative superiority in equipment and pilot skill could offset America's industrial advantage. This belief proved disastrously wrong. By 1944, America was producing aircraft and training pilots at rates Japan could not approach. Each Zero destroyed represented an irreplaceable loss. Each American fighter destroyed was replaced within weeks by a newer, better aircraft flown by a pilot with more training hours than his predecessor. The Zero's legacy is complex. It represented a remarkable achievement in aeronautical engineering, proof that innovative design could overcome limitations in engine power and industrial capacity. Horikoshi's team created an aircraft that met seemingly impossible specifications and performed exactly as designed. But the design reflected tactical assumptions that became obsolete within 2 years of the aircraft's combat debut. The Zero succeeded brilliantly at the mission it was designed for, but that mission represented only the opening phase of a war that lasted for years and transformed beyond recognition. Western historians and aviation enthusiasts remember the Zero primarily as the aircraft that dominated the Pacific War's opening phase and then became obsolete. This narrative captures a truth but misses the deeper lesson. The Zero was not obsolete in 1944. It remained a dangerous opponent in the hands of skilled pilots operating within its tactical envelope. But by 1944, Japan no longer had enough skilled pilots, and American fighters no longer operated within the Zero's tactical envelope. The Americans had learned. The Zero taught the US Navy that aircraft design required holistic thinking. A fighter could not optimize a single characteristic at the expense of all others. The F-6F Hellcat and F-4U Corsair represented balanced designs that accepted modest compromises in specialized performance to achieve robust capability across multiple mission profiles. They were fast, maneuverable, rugged, heavily armed, and produced in enormous numbers. The Zero could still outturn them, but that advantage became irrelevant when American pilots refused to turn. The Zero also taught lessons about training and doctrine. Japan's pre-war emphasis on creating a small elite cadre of pilots with extraordinary skill levels proved disastrous when those pilots were lost in combat. The Americans mass-produced competent pilots through standardized training programs and supported them with tactical doctrine that emphasized mutual support rather than individual skill. An average American pilot flying tactics that played to his aircraft's strengths could defeat an excellent Japanese pilot flying tactics that played to the Zero's strengths. The technical specifications tell part of the story. The A6M Zero weighed 6,164 pounds fully loaded and developed 925 horsepower, yielding a power-to-weight ratio of 0.150 horsepower per pound. The F6F5 Hellcat weighed 12,598 pounds and developed 2,000 horsepower, yielding a power-to-weight ratio of 0.159 horsepower per pound. The Hellcat's superior power-to-weight ratio, combined with more efficient propeller and aerodynamic design, gave it better energy performance despite weighing twice as much. But specifications cannot capture the human dimension. The Zero pilots who attacked Pearl Harbor, who fought over China and the Philippines and New Guinea, were among the most skilled combat aviators of their generation. They flew an aircraft that amplified their abilities and supported aggressive tactics. They achieved kill ratios that would not be matched until jet fighters with guided missiles entered service. And they were systematically destroyed by an opponent who learned from every engagement and brought overwhelming material resources to bear. By war's end, Japan had produced approximately 10,815 Zeros in all variants. The United States produced approximately 12,275 F-6F Hellcats and 12,571 F-4U Corsairs, along with thousands of other fighter types. The production numbers reflect industrial capacity but also design philosophy. The Zero was difficult to manufacture, requiring skilled craftsmen to work with lightweight alloys using precise tolerances. The Hellcat was designed for mass production, with parts that could be manufactured on standard machine tools and assembled by semi-skilled workers. The final irony is that the Zero's greatest success ensured its ultimate failure. Its dominance in the war's opening months convinced Japanese military leadership that their approach was correct. The doctrine, the training system, the aircraft design philosophy, All were validated by victory. This validation prevented fundamental reassessment until the strategic situation had deteriorated beyond recovery. By the time Japanese planners recognized that the Zero needed replacement, they lacked the time, resources, and industrial capacity to develop and field the next-generation fighter that might have prolonged the contest. The Zero story is often framed as triumph followed by obsolescence. The more accurate framing is optimization followed by environment shift. Horikoshi's team optimized for a specific set of requirements that reflected Japanese naval doctrine in 1937. They succeeded completely. The aircraft performed exactly as designed and supported Japanese naval operations with devastating effect. But war is a dialectical process. The opponent learns, adapts, and responds. American fighters evolved to counter the Zero's strengths. American tactics evolved to avoid the Zero's advantages. American pilots evolved through training programs that emphasized the specific skills needed to survive Zero attacks and exploit Zero vulnerabilities. The Zero did not become obsolete. The tactical environment evolved beyond the envelope within which the Zero's advantages mattered. That distinction is important because it highlights a truth that applies beyond aviation history. Optimization for current conditions creates vulnerability to changed conditions. The more extreme the optimization, the greater the vulnerability. Horikoshi's decision to eliminate armor and self-sealing tanks made perfect sense in 1937, when the priority was range and maneuverability. It made the Zero vulnerable when the combat environment shifted to high-speed slashing attacks where pilot survival depended on the ability to absorb battle damage. The Americans learned this lesson and applied it in their next generation of fighters. The F-8F Bearcat, developed late in the war, combined lightweight with powerful engine and retained armor protection and self-sealing tanks. It achieved performance approaching the Zeros in some regimes while maintaining the survivability American doctrine required. The design represented synthesis rather than optimization, balance rather than extremes. The Zero's technical legacy can be seen in post-war Japanese aviation. When Japan rebuilt its aircraft industry in the 1950s and 1960s, companies like Mitsubishi Heavy Industries applied lessons learned during the war. They focused on reliability, manufacturability, and incremental improvement rather than radical optimization. They developed aircraft like the F-1 fighter and later the F-2, which were solid, capable designs that met specifications without pushing boundaries. The philosophy had changed. The human legacy is more difficult to quantify. The Zero pilots who survived the war carried memories of an aircraft that responded to their commands with precision and allowed them to achieve things they had thought impossible. They also carried memories of friends who died because incendiary rounds ignited unprotected fuel tanks or because 12.7mm bullets penetrated cockpits with no armor to stop them. The experience shaped Japanese thinking about technology and risk in ways that historians are still unpacking. For American pilots and engineers, the Zero represented a wake-up call. The shock of discovering that Japan had developed a world-class fighter forced reassessment of assumptions about industrial capacity, design philosophy, and racial stereotypes. The response demonstrated American strengths, rapid adaptation, systematic analysis, mass production, and a willingness to learn from adversaries. These characteristics would define American military aviation for the remainder of the 20th century. If this story gave you a new way to see the Pacific War, like, share, and subscribe, and tell us which moment surprised you most. We'll return next week with another chapter in the war that changed the world.